Good afternoon, everyone. This is about exactly the midpoint of the conference, which is just a thing to note, I guess. Thanks for coming. This talk is adapted from a 90-minute talk, but it's in sections, so probably have to skip a couple of sections, and that's fine. So I can give my usual disclaimers. All the code you'll see is platonically correct, but it might have suffered some slide translation. Please do ask questions if you have them as we go. I will try to keep an eye on time. Like I said, this talk is likely to run the full hour. My goal today, and as in many of my talks, is to enable you perhaps to think a little differently about the code you have. So let's get started for fans of functional programming everywhere. So I'm going to do a quick refresher on functors and monads in general, and then we'll see where applicative fits. Applicative functor is a functional pattern, and it fits in with functors and monads. So first, I'd like to do a quick survey. How many people can answer yes to one of these questions? People who've heard of these functional patterns, but that's about all. Okay, a good amount, maybe half the room. People who understand how they work? Yeah? Good. People who know that, but don't see many use cases for them in their code? Yeah, one or two only. People who've written code that uses them and it was good? Yes, Tristan and the usual suspects. People who completely understand them? Nobody? Anyone say yes to this? Okay, or maybe you have it. Maybe you've had this experience as well. Well, I thought I knew about them until you just said that. Now I'm not so sure. Anyway, in this talk, what I would encourage you to think about is not sort of what these patterns are, because it's hard to get a handle on that, but just we're going to focus on what they do, what they're used for in actual code. So here is a review. A functor is, in C++, a parameterized type, a class template, with one argument free. So, the canonical example is std optional, and I'll be using std optional interchangeably in some examples, so when I say that, you can think any functor. Sequences in general are also functors, and expected is a functor, typically where we bind the error type and leave the expected value type free. So then it's like a class template of one argument, we might say. And the characteristic function on functors is fmap, which enables us to take a function and apply it to the thing inside the functor, right? In C++, it looks something like this. But this is a bunch of syntax. What I'm going to be using in this talk is Haskell function signatures. And I'm going to teach you how to read them. It's really simple, because they are much simpler. So this is just a function prototype, if you like. And this is saying that a function, func, the two colons means has type, and then we've got several things and they're separated by arrows. The last of those things is the return type, and everything else is the argument types, the parameter types of the function. And in C++, where we would have angle brackets, Haskell has nothing. It just has, so f is like our class template here. A arrow b there is itself a function type, a function from A that returns a B. And then we've got f of A, that's like optional of int, where f is optional and A is int, the value type inside the optional. And then the return type is f of B, again a functor type like optional. Okay, so functors have fmap. Monads are very much like functors. Oftentimes, a functor is a monad. Every monad is also a functor, but not necessarily the other way around. And so the usual suspects in C++ happen also to be monads. Also, a parameterized type, i.e. a class template of one free argument. Things like optional, vector, expected. And the characteristic function on monads is, there are a couple of ways to formulate it. Oftentimes we would say bind. Join is another potential. In C++, this is what bind looks like. So it's the same signature as fmap, except that What that function returns, what that f returns, is not a normal type, but a functorial type, so an optional, right? Rather than returning, say, an int, f would return optional int. Here's that type signature in the Haskell notation. Bind is spelt with that funny glyph. And this time we say M because it's a monad, right? So monad of A, optional A, and the function from A's to optional B's, and it gives us back an optional B this time, not just A. I mean, the function in the middle gives us back an optional B, right? So if we combine fmap and join, that is equivalent to bind. So if we have a function that returns an optional, and we apply it to a thing already inside an optional, then we're going to get out of it an optional of optional, right? And join is what collapses down those two optionals to the one optional again. So that is, this is hopefully, how many people, this is sort of a refresher review? Maybe a quarter of the room, maybe a little less. Okay. Well, I'll spend a little bit longer on this and if folks have questions. Okay, so fmap, we know it takes a function and an optional A, let's say, returns an optional B, right? Bind here, the third one down. I've just flipped the arguments around to show it as it's sort of compared to fmap. Bind, the function returns an optional B, right? That A to MB. Optional is the M, remember? And then it takes an optional A, and we get an optional B out. So you can see there that fmap and bind have the same sort of signatures. They only differ in what that function returns that we pass in. And in C++, in C++23, we get monadic functions for std optional, and indeed for std expected. And we call fmap transform. So this is a member function on optional in C++23. And this is directly from CppReference.com, which is probably directly from the standard. So if this contains a value, if the optional is engaged, we'll invoke the f with the contained value as an argument, and then we'll get the optional that is the result type of f. And if the optional is not engaged, it stays empty. The function does nothing, we get an empty optional. But we get an empty optional of the same return type that f returns, right? So this is transform, this is fmap in functional speak. And bind is, we call it and then, right? It's another member function on optional in C++23. And you can see this text is basically the same. If I flip back and forward, the only difference is that last part. The return type of the function we pass in must be a specialization of std optional, right? So in the transform case, we're returning a regular value from f, and in the and then case, or bind, we're returning an optional value, right? And I'm saying optional, of course, because that's sort of like the canonical example to think about. But as we'll see in this talk, there are many things that satisfy, that are functors, that are monads. Okay, everyone happy with functors and monads, at least as far as that goes? Cool, I'm seeing nods, but then I think, Tristan, you're already au fait with this stuff. Okay, so what's applicative then? Well, if we cast our minds back, so mid-90s in Haskell had two type classes, functor and monad. And they're sort of in this inheritance hierarchy, right? So as I mentioned, every monad is a functor, right? So there's this kind of class hierarchy between them. And Haskell has a few well-known, maybe is like optional, and list is like ranges, and IO. Let's not talk about IO. Anyway, so in 2008, well, in the 2000s, but particularly in a paper in 2008, applicative was popularized. And it's another type class, right? And it has this, at the time, it has this kind of inheritance relationship. So again, applicative is short for applicative functor. So every applicative is a functor. And in fact, every monad is an applicative. And every applicative is a functor. So for a while, there was this class hierarchy, which wasn't really correct in that sense. And so later on, GHC changed the class hierarchy to more accurately reflect the relationship between these patterns, right? So this clearly shows every monad is an applicative functor, every applicative functor is a functor. Okay, and of course in C++, we get these functional patterns, we start talking in modern C++ about functional patterns, we start talking about functor and monad, but we don't start talking much about applicative, which is why I want to give this talk. Okay, so let's look more closely at applicative and applicative in C++. Now, there are a couple of talks, one in particular given by David Sankel, firstly in 2015, repeated here a few years ago. So there are a couple of talks floating around which talk about these patterns. Mostly they talk about functors and monads, right? Mostly they sort of mention applicative in passing. And when they do mention applicative, they always say the same thing, right? They take a Haskell. There's the way that applicative is written in Haskell is the bottom line here, the third line. So the top line, that's fmap. Second line down, that's bind, right? That's our transform. That's our and then. Last line is applicative. So in this case, we have a function inside the optional. That's f of a to b, right? That's a function inside the functor. So optional function. And we've got an optional int, let's say, fa, and we're going to return an optional string fb, let's say. And then the first argument is therefore optional function from int to string. And as a C++ programmer, I see this and I think, like many of you, perhaps, well, when am I ever going to have a function inside an optional? Like, we can use functions as first-class objects, but it's fairly rare that we have this case, and so it's fairly unobvious how this would apply to our code. And the footnote here, that everyone says, everyone introduces applicative with this Haskell pattern, and then they say this footnote, and it can be used to apply functions to more than one argument. Well, what I want to highlight in this talk is that's the whole point of applicative, right? In C++, we have lots of functions of more than one argument, and that's what makes it useful. So what applicative does is it generalizes fmap. It generalizes being able to, because fmap works on functions of one argument, right? fmap1 here is transform, right? Or an optional or whatever. If we have a function of multiple arguments, like 2 arguments or 3 arguments, the equivalent fmap would look different, right? It would look like each of these. And in fact, if we go the other way to fmap0, well, that looks like the optional constructor, sort of the degenerate case. Now, the reason it looks like this in Haskell, the reason people say it applies a function inside the functor is because of the way Haskell works. In particular, because Haskell has built-in partial application and/or curried functions, right? And so in Haskell, it makes sense to say all functions only take one argument. And if you have a function of multiple arguments, what you actually have is a function that when you bind one argument, it will give you back a function of one less argument, right? And that's why it has this form, because of Haskell function mechanics. And so this is how it works, right? So when you fmap the plus operation, which is just a binary plus, right, onto a maybe 1, right? Just 1 is like a 1 inside an optional. What you get back is that function inside the functor, right? The +1 function inside the optional, if you like, right? And so in Haskell, that's how it works out. Every time every time you apply, the star glyph here in the angle brackets is the apply or the app function. I'm going to say app sometimes, not to confuse it with std apply, because app is the characteristic function of applicative functor, if you like. So we take plus, we bind one argument. That's just one, right? That's optional int, right? But that's got one argument bound. We bind another, we bind another, we bind. Every time we apply the resulting function inside the functor, we're binding one more argument, right? And this makes sense in a language with built-in partial application. But C++ isn't that way. So in the next part, I will present what I think is a better way to think about this. In making this talk, I went through some of the papers, and they all say much the same thing. They talk about functors, they talk about monads, they don't talk about applicative. So let's have a look at how applicative looks in C++, or how I think it should look. Right? So one of the reasons I made this talk was I saw the following paper, and it's positing a language addition to C++ to allow something like the coalescing operator, so that if things return unexpected results, we can early exit from a computation. So take a look at this function. We've got a couple of functions that return expected results, right? We know that expected is a functor. And then we want to take both of those results from foo and bar and pipe them into a third function. In this case, it's not a unary function, right? It's a binary function. And so today, we might have to do something like this. You know, we run foo, we run bar. If either of them return unexpected results, then we have to exit, right? And we return an unexpected result from strucat here. Now, this problem is also solved today by using various methods. Manual error propagation, like we just saw. Some libraries have macros to deal with it. The only things that have a nice syntax here are exceptions and coroutines, but not everyone can use one or both of those. So I want to try and answer the question without using exceptions, without using coroutines, using applicative functor and getting a nice syntax that's good looking and efficient and declarative. Now, to begin with, I can note that we can solve this problem. We can, of course, because every monad is an applicative, we can solve this problem with the monadic operations, right? We can use and then. And it looks like this mess, where we have to pass through manually the results of calling foo, right? Through to the next lambda, then bar, then through to the next lambda. If they succeed, then we get the inside, okay. But I think this is pretty messy. I wouldn't like to write code like this. I'd like even less to review code like this. Monadic operations tend to not be very declarative. They're about do this, then do this, then do this. That's what we just saw. So an applicative solution, well, if we wanted to go the Haskell route, we might start out by saying, well, let's implement partial application in C++. Well, let's see how that goes. This wall of text is a partial application function. I'm not going to dwell too long on this slide, except just to say that there are two parts. The top part is if we have all the arguments necessary, in which case we go ahead and call the function. And then the bottom part captures those arguments, returns a lambda, which then when we call it, will bind some more arguments. Okay, so I know this is a wall of text. If you don't understand this at first glance, take it on faith or go back later. Let's try that. Okay, so remember, this is what fmap looks like in C++. We're going to have a function, and this time is an optional value, right? And we're going to use that partial application currying function. And we're going to do the obvious thing. Like, if there's an engaged optional, if there's a value there, we can bind that as one of the function arguments, right? And return that potentially partially applied function. And if there's not an optional there in the argument, we'll just return empty optional. Okay? That's fmap. This is apply, right? Almost the same, except that we're taking the function inside the functor, right? And in this case, it's going to be the potentially partially applied function. And we do basically the same thing. We have to check if they're both engaged, in which case we can run the computation. Otherwise, we have to bail with an empty optional. Well, given that, the original code looks like this, right? We can run foo and bar, and now f and b are the returns from those. I'm trying this with optional first, I should say, because optional's a little bit simpler than expected, so let's start with optional. The original was expected, but we'll get there. So now we can fmap, see the bottom line is saying fmap the function L onto f, right? And then take the result of that, which might be unengaged. And now that's a function in a functor, and we're going to apply that to B, right? So this is what it looks like with partial application. Well, you think this looks good? I don't know. It looks a little better than it was, but I'm not happy quite yet. Yeah, it's a little better. It's okay. I'm not yet happy. In C++, of course, we do have functions of more than one argument, which Haskell doesn't. So let's try and do this a different way. Hurrying is not natural. Partial application is not natural for C++. It might be useful sometimes, but I think this is fairly unnatural. So let's try and do it without the partial application. Now, I know that really all functions are functions of one argument, but let's skip over that. So let's try it, take two. In C++, we can have functions of multiple arguments, so why don't we write fmap that way to start with? Okay, let's try and write fmap to take multiple arguments, multiple optionals, right? We've got a variadic pack of optionals here. Well, this is fairly easy to write, like we're just doing the obvious thing. If all of the optionals are engaged, then we can call the function with them all, right? No problem. Otherwise, if any of them are disengaged, well, we can't do anything. We'll have to return unengaged optional. So this, I get to this point in the talk and people say, Ben, I thought you were going to talk about applicative, but you're showing fmap, which is functor. Well, the point of this talk is that we think about applicative in the Haskell way, but this is the reason applicative exists, to apply functions of more than one argument, right? So this is qualitatively different and indeed quantitatively different from transform on optional, because that's a member function, so it only takes the one argument because you're running it on the one object. This is fmap generalized, right, to support applicative. Okay, so take two. When we have this fmap, we can just call it with multiple arguments, right? So we're fmapping the function, which is not inside the functor anymore, right? Because fmap takes a regular function. And f and b are the optional values. Okay, I think that is better, right? The question remains, and I imagine some of you are spotting it, right? In the original code, if foo doesn't succeed, we return right there, right? In this code, we're running both foo and bar no matter what. I see people nodding. Yeah, people were thinking this. They were about to catch me out. I know what you're like. Okay, well, let's address that. Yeah, if foo failed at that point, we don't return here yet. Well, to fix this, we are going to need lazy evaluation. Haskell gets this for free, it's lazy by default, but C++ is not. So we need to figure out a way to evaluate function arguments lazily. Well, what I want is for the call site, I think the best thing we can do in C++ is for the call site to look like the top line here. So I'm going to call fmap, and I'm going to say, give me a lazy call of foo with I, and give me a lazy call of bar with I, right? And so I need some machinery to make that work. Well, what is lazy call? It's just a function that returns a lazy object. And a lazy object is basically a lambda that wraps up the argument and calls it when needed, basically. It actually looks like this. So it's going to capture the function and make space for a result type, right? That's that invoke result t, right? That's the optional that the function's going to return, because we know that these functions return functorial values. When we ask it if it's engaged, that's when it's going to invoke the function and tell us if it has a value, right? And assuming that's true, later on we're going to ask it for that value, and then it's just going to give us that value back when we dereference it. Okay, so this is a simple way to make that lazy. I'm using C++23's deducing this here. This is one of the reasons I wanted deducing this in the language, so that we can get that efficient move out of the object if we want it. Okay, well, with this formulation, now we have, I think, better looking code. You know, maybe you're in a situation where you can afford to call those not lazily. In that case, you don't need to have this, which is slightly more noise, admittedly. But if you're in a situation where you actually want the lazy calls, at least this is the best way I've found to do it so far in C++. Now, the other question that might be occurring to some of you is, does the optimizer actually deal with this? And at least in my experiments, which admittedly are sort of micro benchmarks, as they often are, the optimizer can see through all of this lazy stuff and collapse it down to what we would expect if we wrote it by hand. And so I'm going to say that for this problem at least, this is about as good as I've managed to do so far. I'm open to anyone coming up to me and saying, hey, I've got a new idea, but this is what I've managed to get so far. So that was optional, right? And optional is kind of like functor 101, right? Baby's first functor. It's the maybe or the optional. But let's have a look at what it looks like with expected, because that might be a little more challenging. So here's what the code looks like. I've changed the top line so that now we're dealing with expected rather than optional, right? But otherwise, the call site code is exactly the same, right? All we need to do is implement the machinery for expected. And that's worth saying, again, to people who are new to functional patterns, that the patterns are the same. We can think about them the same, but the implementation of the pattern is different for every functor, right? So fmap on optional is different from fmap in implementation on expected is different from the implementation of fmap on vector, let's say. Okay, let's very quickly extend this to std expected. Well, fmap is going to look much the same at the invocation, but we need to do a little bit more to sort of prepare the types here. So we can pull out the value type of the expected t, right? By saying, well, that's what we get if we just run f over all of the expected values. The error type is a little more fiddly to get. I chose here to just take the common type. Hopefully, all of these expected would use the same error type, right? And I would highly recommend that whenever you're using expected in this way, you should be having the same error type. But, you know, that's not true in general, so I've just used common type t here to get the error t out. And it's worth noting that tx here is going to be not actually a std expected, but our lazy type which wraps the std expected. Right, so that's how I'm exposing the error type. Well, given the t and the e, then the result type is just the expected of those two. And the happy path looks much the same. We're just going to say, if all of these things are engaged, then we can call the function dereferencing all of them, right? And wrap that up in the result type, which is going to be the happy path, the expected value, right? Now, so this is the happy path, and the lazy thing for the happy path looks very similar to optional. So the operator bool is doing the same thing. That's where the function gets invoked. That's where we can say, yes, we have a good value, right? And the dereference similarly Well, we're going to call that if operator bool return true, right? Basically the same. Again, we're hanging on to that invoke result, which now is an expected, stood expected value. And we're just pulling out the error type for the machinery, right? So the happy path looks much the same, not too much more complicated. The unhappy or unexpected path does require a bit more work. Because recall, in that call site, we are using the fold expression, right? So we're only actually evaluating the functions as far as we need to. So when we get the unhappy path, we can't be dereferencing anything that we haven't evaluated the function for. So the approach I took was just to sort of use another fold expression. Instead of and, use an or, and just write a simple inverter type to flip the types that came back from the function. So the inverter type wraps the actual stood expected, right? And if the expected is not engaged, then the inverter returns true, or vice versa, right? And it will get the error when we ask for it. And then the calling code looks like this. We wrap the result in the invert. That's the second to last line here, right? We're passing invert to this extract error, and that's in a fold expression. So we are basically folding over something went wrong, right, in the and expression. And so we only want to evaluate the error that actually went wrong, you know, the error that went wrong. So up until that, it's all kind of, all the inversions are false because they all succeeded, right? And when we hit the inversion, when we hit the one that failed, that's where the invert returns true and gives us that error out. Is that clear? People follow that? Hopefully, I'm seeing some nods, I'm seeing some people thinking. Okay. All right, anyway, the high level is we have the same kind of structure. And so the call site looks exactly the same, right? This time fmap is fmap for expected instead of fmap for optional. Foo and bar are returning expecteds instead of optionals. But the calling code is just the same. And that's kind of what we want. That's kind of what we want from functional patterns. We want that code to look nice and be as efficient as we can make it under the hood. So the question is, does the optimizer still, it sees through optional, right? Does it still see through expected? Well, again, the answer happily is yes in my experiments. Okay, so conclusion from this. Does C++ need an error propagation operator, as that paper says? Well, I would say the answer is a solid maybe. Like, I wrote comparatively a lot of machinery to make this work. C++ is full of library solutions that might be better in the language. So I'm not going to say to Barry, who wrote the paper, that we don't need this. But when we have this conversation, we need to be thinking about these kind of things because, you know, this is why I'm giving this talk, because this is what applicative is for, right? We need to be aware of the solutions in functional patterns, right? So we know fmap, we know bind, but we've comparatively forgotten about applicative. It's for variadic fmap. Okay, so I'm claiming that this variadic fmap is the same as applying a function inside an optional. Is that claim true? Am I entitled to claim that? Well, the way to show that is to implement the one in terms of the other, right? Now we've seen how, you know, and we know from Haskell how the function inside the functor interpretation implements variadic fmap with the partial application, you know. So we know that that can implement our formulation, but we need to show vice versa for my claim to hold true, right? Well, happily, it's quite straightforward to implement classical apply with variadic fmap, because all we need to do is fmap stood invoke, right? Std invoke is going to take function inside an optional, argument inside an optional, other argument inside an optional, and it's going to invoke, apply is, so fmap is, our variadic fmap is going to call std invoke on the result of unwrapping all those optionals, i.e. the first argument is our function inside the functor, so it's going to invoke that function on the optionals, right? So this is the same thing. And the bottom of the slide is the same thing in Haskell, except C++ has a superpower, which is variadics, right? Haskell, vanilla Haskell, doesn't have that. So they actually can't do this as easily, right? They can't do this generically like we can. They have overloads for 2 arguments, and maybe even overloads for 3 arguments. And sure, you can make an overload for n arguments if you need it. But we can do this in one function with a variadic template. Cool. All right, that's optional. That's expected. That's a little use case. I want to talk more about, how we should think about applicative versus monad. Because, I said every monad is an applicative. And we have functors in the standard now, and we have monads in the standard. So, we should ask, why do I need to care about applicative? Why can't I just use monad, right? And it's true that every monad is an applicative, and monad is therefore sort of more powerful than applicative, and certainly you can do everything with monad that you can do with applicative. But, this was the messy code that I showed. Like, this does the same job. This is the monadic formulation where we have to nest and then, and then, and then. And yeah, maybe this would look better with a form of do notation like Haskell has, or some kind of pipeline operator. But it's still doing the nesting. It's still actually very non-declarative. It's very procedural, right? It's saying do X, then do Y, then do Z, etc. And that's really what monad is for, right? That's how we should think of monad. It's for when you need to make choice based on what came before. In other words, that computation is inherently serial, right? It's procedural, it's serial. You're taking the result of one function, passing it into the next, then taking that result, passing it to the next. Applicative is different. Applicative is inherently parallel, right? Now, I showed fmap, variadic fmap, and we have a fold expression. And of course, we know, like fold expressions are sort of short-circuiting and serial, but that's an engineering choice here, right? All of these this function applied to all of these arguments, or what's inside these arguments, evaluating the engagedness of all those optionals. It's an engineering choice whether we do that in parallel or not. Like, they're all independent at that point. That computation could run in parallel, right? That's the fundamental difference between monad and applicative. So, and when I was sort of learning Haskell and learning functional programming, or coming back to it after a period of, since university, this is how I heard functional programmers thinking about architecture. Do I need the serial nature? Do I have a computation later on that depends on the result of the computation before? If so, I know I kind of need a monad. But if I can run things in parallel, then I only need applicative, right? And if you only need applicative, it's a better situation than using a full monad, right? Okay, so we saw optional, we saw expected. Let's take a look at a few more examples of applicative in C++. So ranges, sequences in general, ranges in C++ are functors, right? We know that. We have transform. We've had transform since C++ 98. That's basically the implementation of fmap, where the functor is the vector or the array or the range in general, right? And so, so here we have a bunch of ints, and we're fmapping the square function into the sequence, into the range, and we get a range of squares, right? And we know also that a range is a monad. In fact, in C++ 20, or I think 20, we have transform and join. Certainly if not 20, then 23. We have range functions called transform and join. Thank you, Tristan, for confirming. And so, if we have a monadic operation like, min-maxing a chess game, right? We have, given a board position, we can compute the next board positions possible, right? That's taking a board and giving us back a range of boards. If we want to proceed to the next turn after that, then we need to, again, run that next position function on all of those boards in that range. And that's going to give us a range of ranges, which we're then going to join, right? So we're using bind. Bind is transform followed by join, or fmap followed by join. Okay, so ranges are functors. Ranges are monads. We know that every monad is an applicative, right? At this point, we're perhaps prepared to take this on faith. But so let's ask the question, how is range an applicative, right? If we know it's a monad, it must be an applicative somehow. So what's the answer here? How would we write the characteristic function, the apply function? We need a function that takes a range of functions, right? In the classical formulation, the function in the functor here is going to be a range of functions and applies those to a range of values, right? Or alternatively, a function that takes a function of n values and n ranges, right? The variadic formulation I showed. Okay, well, we have a function in C++ that takes a range of functions and a range of arguments and applies the functions to the arguments. Zip transform might spring to mind for several of you. And this is applying a function of multiple arguments over multiple ranges. It's zipping the ranges together, applying the function to each range position. So we have a function that does this. Is this function going to give us, implement apply as an applicative functor? So it is going to give us the applicative functor, sorry. Is that also a monad? Because one of the things we have to check here is there might be several formulations of applicative, and there might be several formulations of monad. We need to check that the one we chose also leads to a monad. So if we go through the types, we're going to find that it actually doesn't fulfill the monad laws, which I won't say much about, but usually what we run afoul of is associativity. In some way, these operations need to be associative. If we have a range of functions and a range of arguments, then we have a range of ranges. We can't just join those together because we run afoul of associativity here. So let's try again. So zip transform gives us one formulation of apply on ranges, but that is not a monad also. Now there's another function with almost this signature, which is Cartesian product, right? It doesn't take a function, but the implicit function applied is make tuple, right? It's going to zip together these ranges every which way, give us the Cartesian product of, and it's going to be a range of tuples. And Cartesian product does actually fulfill the monad laws. So yeah, when we do Cartesian product on 1, 2, 3, and ABC, we get the tuples 1A, 1B, 1C, 2A, 2B, 2C, etc. Happily, if we have a function that gives us back ranges, and we run the Cartesian product, and then we join them together, that does fulfill the monad laws. So Cartesian product view, zip transform view, gives us the applicative functor on ranges, but not a monad. Cartesian product view also gives a different applicative functor formulation, and that also is a monad. And we find that if we just, so here we have multiple ranges and a function, and we're going to get the range of tuples back, right? And then we could apply that function by just mapping apply over the tuple, right? The Cartesian product of the ranges gives us the A1, B1 followed by A1, B2. And then if we run the function on those tuples by f-mapping apply over it, we will get a range of ranges. And if we just join that range of ranges, then what we've just done is implement monadic bind, right? And that fulfills all the monad laws required. Okay. Now, in case it escaped your notice, C++23 therefore has list comprehensions, right? List comprehensions are, in Haskell, implemented by applicative on lists, by Cartesian products. They result in Cartesian products. So here's Haskell, here's Python, or Python and Haskell, and here's the C++ equivalent. We have list comprehensions, they just look horrible from a syntax point of view, but they are exactly the same thing. They give the same results, we don't have the syntax for them. But that's exactly what a list comprehension is. It's an implementation of applicative on ranges or lists. Okay. Yeah, they're a bit verbose. Now the next section I think I'm going to skip. I will go through the slides, but mostly for the video. So we can write Cartesian product for ranges, and folks like Tristan have. We can also think about ranges of heterogeneous elements, i.e. tuples, right? So can we write Cartesian product for tuple? Yes. And here is what the result looks like. So we have a tuple of A, 1, and true, right? And then we have a tuple of X and 3.14. When we do the Cartesian product of those, we're going to get a tuple of tuples, each of which has an element from the first and an element from the second. It looks the same as ranges, except now they're heterogeneous collections, right? And if we do a Cartesian product, we can look at this as happening recursively. So the sketch of the recursive algorithm is something like this. If we split the tuples into first and rest, and we say, let C be the Cartesian product of the rest, right? This is a classical recursive algorithm. As you can say, we know how to do this on the rest, right? That's the recursive step. We're going to take each element out of the first tuple and prepend it to each tuple in the rest that we got from the Cartesian product. And that's how the recursion proceeds. And then if there are no tuples left, we're actually going to return a tuple of one empty tuple, because that is the way that this shakes out in the recursive formulation, right? That bottom line there. So you can see that the tuples shrink down, the outer tuple stays, so that the result of the recursion in the base case is actually not just an empty tuple, but a tuple containing one empty tuple. Anyway, that's how it goes. This is what it looks like. You're not expected to understand this at the first glance. But you can see there's the base case at the top, tuple of one empty tuple. The recursive step is shortly below that. We're doing the Cartesian product of the rest. And then the rest of this stuff is just doing the mechanics of taking the tuple element and putting them on the front and doing that stuff. Yeah, so that's that. Of course, there we've done the same thing as Cartesian product on ranges, which is that the implicit function where f-mapping is make tuple, right? But there's no reason a priori that should be the case. We could f-map a different function. And we can do that just the same, right? In this case, we need sort of a flip version of currying. to apply the arguments in reverse order. Because of the recursion, we end up building up from the base case and binding the arguments from the back. This is just like what we saw earlier, except with some arguments reversed. And this is just like what you saw before, except instead of make tuple, we are now calling the function rather than. So if I flip between these two slides, you can see in the middle, this is the version with tuple cat. So we're returning a tuple on the inside, and here's the version of just calling subs, right? So that's the function application generalization. Phew. Anyway, that was just an aside, and I wanted to just show that, but kind of skip over it, and it's available. I can talk to you later about it. What I want to go back to now, just in the remaining time, is just highlight a few more uses of applicative and where it came from. One of the original uses in that 2008 paper was for parsing. A parser for things is a function from strings to lists of pairs of things and strings. This is a quote. What that means is, a parser for things, like ints, I'm going to take a string, it's a function from a string, and what am I going to get back? A list or a range of pairs of things and strings. So a pair of a thing and a string is the thing I parsed out and the rest, what was left over on the string, right? That's the pair of thing and string. And it's a range or a list of those because there might be more than one way to do the parse, right? Oftentimes we think of it just as a list of at most one element or an optional, right? So the parse either succeeded or it failed, right? An optional is like a list of at most one element. So, when Jason and I did context for all the things, this was how I thought about it. This was how I knew it was possible, right? And I wrote this function to combine two parsers. What this does is it runs the first parser, it runs the second parser, it takes those results and combines them with a function. That looks a lot like fmap of a two-argument function, does it not? That looks a lot like a version of applicative. In fact, that's exactly what it is. It's fmap2, if you like. That was super useful. And in that talk back in 2017, I mostly used it in two flavors, actually, just to throw away one side or throw away the other side, which I used overloaded less than and greater than operators for, so that I could write code that looked like this. I'm combining parsers using that function, which is a type of a formulation of applicative, so like a two-argument function. Quote, if I want to parse a string, what I'm actually going to do is parse a quote, then parse a bunch of things that aren't quotes, and then finally parse another quote. And I don't care to keep the quotes because I know that this is a string, right? I know strings are surrounded by quotes. Now, I give you one guess where I learned this technique. I didn't make it up out of whole cloth in 2017. Funnily enough, Haskell has these functions that do exactly this. They combine two functorial values, throwing away what's on the left or throwing away what's on the right. That's all it is. And exactly the same in C++. So now to contrast what it looks like with a monadic approach versus an applicative approach. When we parse using a monadic approach, we have this characteristic procedural type of thing happening. So if we're parsing, in this case, a two-digit hex number, we're going to parse the 0x, then we're going to parse the first digit and call that the high nibble, then we're going to parse the second digit and call that the low nibble, then we're going to put those together with a hexify function, right? And what we've got is a parser for two-digit hex numbers. And if we were to write this in C++, it would be a horrific chain of and then, and then, and then, and then, right? Nested, 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 nested. What does it look like with applicative? Well, in applicative, it looks like that hexify function, that function which actually puts together the values, we're going to apply that, right? That's our first argument to apply. What's our next argument? It's actually a sub sort of combination of parsing OX, but then throwing that away and parsing the first hex digit, and the second argument is going to be parsing the second hex digit, right? So this is in one line using applicative style, and I'm showing this in Haskell because it's much more easy to fit on the slide, right? But in C++, you can imagine, like I said, this would be a horrific nested and this would be, you know, not much different from the example I showed earlier. So the conclusion here is, you know, when you're parsing things, unless you're parsing C++, applicative is, for any sensible grammar, applicative is often all you need. You don't actually, if you don't have context-sensitive parsing, you don't have that monadic thing of, you know, the parser you're running is not going to depend on what you parsed before if you don't have a context-sensitive grammar. If you have a regular grammar, or, you know, LL1 or whatever, you can use applicative, and you don't need the monad. You don't need that inherent seriality of the monad. Okay, I have a few minutes. I just want to highlight one more thing coming to C++. P2300 is a paper, you may have heard of senders and receivers. This is a model for asynchronous execution. I've read P2300, I've implemented a bunch of it. I'm pretty sure the authors made a conscious decision to excise any functional terms from the vocabulary in that paper, which means that people like me have to go fishing for them. This is from Eric's talk, and these are some of the combinators, some of the sender adapters from the paper. Now, if we know what we're looking for, we can identify the functional patterns in here. Because then takes a function and it applies that function. It transforms the value of the operation with the function. Well, that sounds a lot like fmap, doesn't it? Let value does the same thing, except that you're returning a sender in that case. You're returning a monadic value or a functorial value. That's bind, right? And when all, well, that's taking a bunch of monadic values, of senders, and it's completing when they all complete, and sending all of their results on at once, such that you could run a function on them, right? That sounds like variadic fmap or apply. And that is indeed the case, right? The P2300 calls them then, let value, when all, and just is like the pure operation. It lifts the value, it makes a sender from the value. It's like a optional constructor, right? It makes the functorial value from the regular value. And this is how we know that P2300 is a sound design, right? Because if you pull back the curtain and look at these things, you see that they're built on fundamental, solid, functional patterns that we've known about for decades. And so we know that it has the expressive power to solve problems. Now, just to finish up, I think more than any other example, P2300 highlights the difference between monad and applicative, because P2300 is all about concurrency, right? You could implement when all with the monadic operation. You could implement when all with let value. If you did that, you would have to serialize all of those concurrent operations. It would sort of obviously be wrong, right? Why would you do that in the context of a concurrency library when all of the input senders are running in parallel, right? And that's the difference between monad and applicative, right? If you don't need that monad, you can get by with applicative, and the engineering choice is there to run it in parallel. Okay, I think that's definitely all I have time for. I don't really have time for questions, but you can find me in the hallway. In conclusion, I hope I've shown in this talk, I've shone a light on applicative. I've shown in particular how it's different from monad, and in particular how thinking about it in the Haskell formulation is not too useful for C++, and there are better ways we can think about it. We do have a bunch of monadic, functorial, applicative things in C++, and more coming down the pipe. So thank you very much.